Good day, I am Reflex Rodriguez of class 5-2-954, and today I am going to present my chemistry lab report summary for experiments 1, 2, and 3. Experiment number 1, Precision and Significant Figures. Measurements are being made every second in the scientific world. Because of its prevalence in the field, it is important that we practice accuracy and precision in every measurement that we perform. This is to avoid any accident that might happen. However, no measuring tool could precisely or accurately provide us with exact measurements of the materials that we measure. Thus, it is important to take into account the level of uncertainty that each measuring tool have in order to provide a more reliable set of data for scientific endeavors. The objective of this lab experiment is to practice recording measurements with the correct precision. The experiment provided the learners with different photos of measuring tools which had certain measurements in it. These measuring tools include the burette, the Erlenmeyer flask, the graduated cylinder, the beaker, and the meter stick. The learners had to determine the measurement given in the photos of the measuring tools. Also, they have to determine the significant figures based on the measurement that they have recorded. After performing the experiment and collecting the results and data, I have come to the conclusion that it is important to take into account the level of uncertainties that each specific measuring tool provides. This helps us have a more realistic approximate of the measurement that we desire to achieve. Also, according to LibreText 2020, it is also essential to put into mind that there will always be errors due to the limitations in our measuring tools and our own senses. Experiment number 2. Heat of combustion. Organic compounds burn or go through the process of combustion to produce energy. This energy is often used for multiple purposes. More recently, the usage of ethanol as fuel has increased thanks to its renewability. And so, one must be curious about the qualities of good fuel. Substances that when burnt gives out large amounts of energy are good fuel. But is there a relationship between the energy released by one alcohol and another alcohol? This experiment aims to determine the relationship between the heat of combustion and number of carbon atoms in an alcohol chain. For the results and data of this experiment, the first table that we have is the data table for heat of combustion, or the theoretical data. As you can see, there are 6 kinds of alcohol that is being compared. These alcohols are methanol, ethanol, propanol, butanol, pentanol, and hexanol. As you can see, they have different numbers of carbon atoms. From methanol to hexanol, it increases by 1 to a maximum of 6 carbon atoms. They also have different bond energy requirements for the breaking and bond energy requirements for making. And then, these two sets of numbers are added in order to have the energy change, or the kilojoules per mole. The next 2 tables show the data table for heat of combustion from the experiment. This experiment in particular was performed already and is provided to the learners for a virtual setup. These 2 tables are set 1 and set 2. As we can see, these alcohols are the same alcohols from the previous slide, and their mass inside the burner is being compared before and after the combustion. The mass of the alcohol is also compared, their initial temperature as well, and their final temperature. Also, the temperature change in it. The table 4 shows the summary of data from the previous tables. The first row introduces the alcohols and the different kinds of alcohols compared in the experiment. The next row compares their combustion in joules, which is all the same at negative 20,000. And then the third row compares the mass of burnt alcohol. As we can see, it decreases from left to right, from methanol down to hexanol. The same can be said towards the moles of burnt alcohol and the delta H combustion per kilojoules per mole. Post-lab questions. Compare the heat of combustion of the alcohols. Rank the heat of combustion of the different alcohol in increasing order. As we've seen from the tables earlier, the heat of combustion in increasing order is as follows: methanol, ethanol, propanol, butanol, pentanol, and hexanol, the exact same order as they were in the table, from left to right. Number 2. Rank the different alcohols in increasing number of carbon atoms. The number of carbon atoms increases from methanol, ethanol, propanol, butanol, pentanol, and hexanol. As we have noticed, it is all the same exact order as the previously mentioned orders of the alcohol. And finally, number 3, examine the plot for the heat of combustion data. Is there a direct relationship between heat of combustion and number of carbon atoms? Explain. As you can see, I have plotted my own graph comparing the number of carbon atoms with its heat of combustion. As we can see, the heat of combustion is in delta H, or kilojoules per mole, and then the number of carbon atoms is in numbers, of course. And so there is a direct relationship between the heat of combustion and number of carbon atoms. The more carbon atoms an alcohol has, the higher heat of combustion is yielded. Therefore, we see a direct proportion in between direct relationship between the heat of combustion and number of carbon atoms. Experiment number 3. Calorimetry. Heat energy constantly evolves in nearly all chemical and physical processes in nature. In laboratory experiments, the chemical reaction's heat flow is often measured in an apparatus known as a calorimeter. Calorimetry is a heat measurement technique used to determine the amount of heat that flows into or out of the surroundings. A calorimeter consists of an insulated container, a thermometer, water, and a system to be studied or experimented. In this experiment, a styrofoam cup will be used in order to allow us to presume that no heat is being transferred through the calorimeter walls. The heat flow of a chemical reaction is also quantitatively expressed as the heat of the reaction, delta H. Negative delta H means that reaction is exothermic, where the heat is evolved, and positive delta H means the reaction is endothermic, where heat is absorbed. In this experiment, we aim to observe how changing variables affects the initial and or final temperature and amount of heat exchanged in a constant pressure calorimeter experiment. Part A shows the table validating the assumption. We can see the weight of the cold water along with its initial temperature, the same with the hot water's weight and initial temperature, and the final temperature of the calorimeter. We also have the specific heat of water. And so for the summary of data for part A, we can notice that they both have the same weight and temperature. However, they have different amounts of heat here in this table, with the cold water at 4,180 joules and the hot water at negative 4,180 joules. Question 1. When the cold and warm water are mixed, do you expect the change in temperature of cold water and warm water to have the same value or different values? What about the amount of heat present in cold water and warm water? Explain your answer. I am expecting that the changes of temperature for the cold water and warm water to be the same, because as the warm water is poured into the calorimeter, its heat transfers to the cold water. At the same time, the amount of heat present in the cold and warm water would be of the same magnitude, because the energy gained by the cold water is equal to the energy lost of the warm water. Table B shows the results and data from the second part of the experiment, where an unknown metal is to be identified using calorimetry. And so, looking at the summary of data for part B, we can see that the probable identity of the metal is tin. Question number 3. When the metal and water are mixed, do you expect delta T metal and delta T water to be the same or different? Explain. I expect the changes in their temperatures to be different because unlike Part A, where water of different temperatures was combined, Part B combines two materials with different specific heat capacities, namely the metal and the water. And so, as the metal was placed in the water, its heat transferred to the water or its surroundings, showing an exothermic process. Question number 4. When the metal and water are mixed, do you expect Q metal and Q water to be the same or different? Explain. It is expected that the magnitude of their heat will be the same because the energy lost by the system must be equal to the energy gained by its surroundings and vice versa. In part C of this experiment, we can see that two chemicals have been used in order to test calorimetry. We have NaOH, or sodium hydroxide, and HCl, or hydrochloric acid. In this activity, there were three setups made involving calorimetry. For part A, the heat transfer between two materials, or water, of different temperatures was studied. Since they have the same specific heat capacity, it is expected that their respective change in temperature would be the same. For part B, an unspecified metal was dropped in the calorimeter. The heat transfer between a system and its surroundings was studied. When a system releases heat, it is said to be an exothermic reaction. When a system absorbs heat, it is said to be an endothermic reaction. The experiment also proved that one can determine the specific heat capacity of material through calorimetry. Finally, Part C was an example of neutralization, where an acid was combined with a base to produce water and heat. The calorimeter allowed for the heat released during the neutralization to be properly observed. And that concludes my presentation for my chemistry lab report summary of experiments 1, 2, and 3. Thank you very much and God bless.